Hi, my name is Alfonso Campos, and today I will explain the experiment of the electrical equivalence of heat. As we saw in the previous experiment, we can calculate the conversion factor between joules and calories using this formula right here, which is the change in potential energy is equal to heat minus the work. This formula essentially tells us that the energy is conserved in all cases. It cannot be created or destroyed. But in this experiment, we're not going to use work as we did last time. Instead, we're going to use electrical energy. So when you have a circuit, the electricity happens because electrons in that circuit start moving. That is literally what electricity is. So if you have, for example, a filament like this one right here, and you pass the electrons through it, they will crash against its atoms and start heating up. And as you may know, the photons, when an object heats up, any object at any temperature can create some specific light. It creates a spectrum of light. So when it's hot enough, it creates both infrared, visible light, and ultraviolet, as these three are next to each other on the electromagnetic spectrum. Infrared is can be seen as heat, visible light is the light you see, and ultraviolet is just more energetic light. So how we're going to take this into account in order to do the experiment is that we basically want to grab this light, this energy, and put it all in a container, so no energy escapes, and this energy can be transferred as heat. In this case, we'll be canceling both the visible light and ultraviolet light just to get heat, and this heat will raise the temperature of a substance, let's say for example water. And when we do this, we can simply calculate just how much electrical energy we use to make this light happen, and therefore we can simply we can get an estimation of the conversion of electrical energy that we use to power up this bulb to the heat which hit the system, and therefore we have a system where both the electrical energy and the heat are the same, and therefore we can get the conversion factor between joules and calories. So exactly how we're going to do this is we're going to use this formula for electrical energy. As you can see, electrical energy is equal to the power times the change in time. But power can also be calculated by voltage times current. So therefore, what we can do is simply power up the bulb with some power generator, and record with two multimeters both its voltage and its current. And to change the time, we can just put a chronometer to know that. So here is basically what the experiment is. Here we have a bulb. In the bulb, there's going to be some ink. This ink will block the visible light and the ultraviolet one. So the water the bulb will be submerged in water, and this water will absorb all of the heat, therefore making the temperature higher. We're going to put all of this in a calometer, which is the best thing we have to a container that doesn't transfer energy to the outside. But we also need to take into account how much energy it exchanges in order to get a more accurate result. For the heat, we're going to use this formula, which is the mass of the water plus the mass of the calometer times the specific heat of water times the change in temperature. So as we're going to try to get heat in calories, we're going to use the heat of water in calories, which is exactly 1 calorie per gram per centigrade. Is the definition of a calorie. So therefore we need the voltage, the current, the change in time, the mass of the water, the mass of the calometer, the final temperature, and the initial temperature. We're also going to record the ambient temperature in order to get a more accurate result. I will talk about that later. So therefore, the final formula is this one right here, on which the conversion factor between calories and joules will just be the electrical energy divided by the heat. And our theoretical value, the accepted value, is 4.184 joules per calorie. So our objective is to try to get this number. So here is basically how the experiment is. As you can see, here is the calometer plus the water plus the bulb. The power supply, it powers up the bulb. We have a voltmeter and an ammeter, seeing both the voltage and the current. We also have a chronometer, which will tell us the change of time. And we also have a thermometer right here, which will record the temperatures, the initial, final one, and as well as the ambient temperature at the start of the experiment. So here is how the experiment is made. As you can see, here is the calometer. In this calometer, inside it's this this right here, which is the water with the ink already put on it. And here is the top of this container, which contains the bulb itself with some cables in order to connect it to the power supply. So here is basically how most of the experiment is. Here is the balance you can see we use to record all of the masses. So first of all, we put the calometer in the balance to know how much its mass is. Then we put the water and the ink in the container and the top. So then we calculate the mass. Well, we weighted all of it. From there, we can just subtract masses to get the mass of the water itself. Here we have the power supply. As you can see, it's connected to an ammeter, which tells us the current, and the voltmeter, which tells us the voltage. We're going to take the average values for this because they change somewhat in the experiment, but they don't vary a lot. So we're going to take just the most common values. Here you can see the thermometer. In this part of the experiment, as you can see, both the ambient temperature and the initial temperature have been recorded. We're just waiting for all of these to get to the equilibrium temperature, not to get the final temperature. And you can see here is a cell phone, which is right now acting as the chronometer and taking the time, counting the seconds it takes in order to get to the final equilibrium temperature. How we know this is the equilibrium temperature is because we just see that the thermometer doesn't change anymore. So therefore, here is all our data we got. As you can see, the ambient temperature is 23 degrees. The mass of the base with the top, which is with the base with the bulb, etc., is the value right here. The mass of the calometer by itself, the mass of everything plus the water, the initial and final temperatures, the current, the voltage, and the change in time. So from both these masses right here, the calometer mass and the mass of the base with top, we can isolate the mass of the water. So we can calculate the mass of the water is around 218.79 grams. Here I'll insert it in units. From this, we can use these two formulas in order to calculate all of it. So remember, for electrical energy, we need the voltage, which is right here, the current, which is right here, and this change of time, which is right here. And as for the heat, we use the mass of the water, which is right here. We already calculated it. The mass of the calometer, which is right here. The specific heat of water, remember, is just 1. And the final initial temperatures, which are these ones right here. The ambient temperature was taken into account because there can be some error if you make the difference in temperature not equal. For example, as you can see here, from 15 degrees to 20 degrees, which is the ambient temperature, is just 8 degrees from difference, and from 23 to 31 is just 8 degrees as well. This was made on purpose because any heat gained or lost to the ambient, because it's at a different temperature, can be somewhat cancelled at the start of the experiment, where the whole system is gaining heat. It's gaining heat from the ambient, And at the end of the experiment, which whenever the system passes the ambient temperature, starts to lose heat to the ambient. So we can cancel both this gain and this lost by making them be at the same distance from the ambient temperature. So therefore, when we take all of this into account, we can get the final values for, well, electric energy and heat, and we divided them to get the exchange factor between calories and joules, which was around 4.3 joules per calorie. For the uncertainties, well, for these ones right here, we're just recorded from the instruments we use. For the rest of them, specifically the water mass and the conversion factor, we simply use the formulas for the derivatives of uncertainties. So basically what we did was, for this first one, used the uncertainty for the sums, well, in this case for the subtractions of these three masses. For the electrical energy, we just took the derivatives and the uncertainties of these three values right here, calculated them correctly, as well as from this one right here and this one right here, and finally divided both of them. I used the uncertainties for the division in order to get this value, around 0.2. So when we compare this to the theoretical value we got, as you can see, it's not that far off. It's just 4.3, and this is 4.1, around 4.2. And as you can even see, the uncertainty actually covers this absolute value. So when we calculate the error, it's just around 3.3%, which is really close. It's a very accurate experiment. So maybe there could be some slight error due to, for example, as we left the thermometer in during the whole experiment, it actually contributed to the gain and loss of heat, and that wasn't taken into account. For example, for the water, we also put it in a container which is made from plastic, and this plastic also contributes to both the gain and loss of heat, and that wasn't also taken into account. But even don't take into account those two errors, we got a pretty accurate result which actually contains the accepted value in its uncertainty. So we can say that this experiment was a success. Here's our reference for the accepted value, and thank you for watching.